All right, so the first part here is scientific methods worksheet, graphical analysis. Guys, also I'm sorry about the little things that got cut off. I went and fixed that in my file. But here we have some data about buying CDs. Is this getting too dated for you guys? Do you ever buy CDs anymore? No. When I was your age, CDs were like the new thing. People used to get tapes. Remember tapes? There's all kinds of secrets about tapes. Anyway, so this is what are the units for the slope of this graph? And so you remember that slope is equal to the change in y divided by the change in x. And so the units for the slope are going to reflect that. So our units for the y here are in dollars. And units for x are in compact discs. So our units for the slope are going to be dollars per compact disc, right? Which is basically how much you're going to pay for each CD. So the slope tells us how much you pay for each compact disc. Write an equation that describes the graph. So when we look at this, we know that it's a line. So it's going to have the form y equals mx plus b, right? Because it's a line. In this graph's case, our y is going to be the cost in dollars. So we replace that. Equals the slope, which here is given to us is 7. So it's $7 per CD times the number of CDs plus the intercept, which was given to us as 3.6. So it's going to be plus $3.6. So even if you had 0 CDs, your cost would be $3.6. That's kind of weird, right? What do you think it could mean? Go ahead, Shannon. Yeah, that could be shipping costs. Maybe this is why we just download things now. You don't have to pay for shipping costs, which is nice. But that could be the base price that you're going to pay regardless of how many CDs that you buy. So yeah, shipping I think is a very reasonable one. You guys have any questions about number 1? We get them all right? Yes. All right. Number 2. Again, this one got cut off. I'm not really sure why that happened. But the following times were measured for spheres of different masses that were pushed a distance of 1.5 meters by a stream. So that's water. The first thing we have to do is graph our data on the grid provided and write a mathematical model or an equation. So here, our spheres were different masses. And so that tells us that the mass was the independent variable, and then the independent variable should go along the bottom. So down on the bottom is where we're going to have mass in kilograms, and our range is going to be from 0 to 20. So I just counted these out real quick. I'm going to go 0, 5, 10, 15, 20. So that spaces them out pretty well so that we can see them. It's a good idea to always have 0, 0 down on the end. One thing that helps you with is making sure that when you draw your line, you can see where your y-intercept should be. If you look at this and you start with 5 here, then your y-intercept would actually be over a little bit, and that may mislead you a little bit about where the intercept should be. On the side, I'm going to put time. I'm just going to rotate this because it's easier. It's easier for me. Time seconds. So this needs to go up to 30. So if I did 10, 20, 30, that would probably work. And you might have a little bit different scale on the side, and that's okay. If you decide that you want each one of these to be 10 and so yours is only half as tall, that should be fine. This thing about 0, 0 is important, but the scale, and there's different ways that you can do that and it'd be okay. All right, so I'm going to graph this data for a mass of 5 kilograms. I had a time that was just over 10, so I'm going to do a dot. I'm going to put a circle around it. For a mass of 10, I'm going to go up to about 17, halfway between 15 and 20. At 15, I'm going to go up to 23. And at 20 kilograms, I'm going to go up to 31. So that looks pretty linear. So I'm going to draw. All right. So an equation for this. Again, this is a line, so it's going to be y equals slope times x plus b. Y is time in seconds. The slope, what is our slope here? If I'm going to calculate my slope, I'm going to do a change in y divided by a change in x. So on the y side, if I use the two furthest data points, we have 31.0 minus 10.2 divided by 20 minus 5. So this is going to give me 20.8 divided by 15. Pulling out a calculator, 20.8 divided by 15. I got 1.4 seconds per kilogram. So I've got 1.4 seconds per kilogram times mass in kilograms plus, and then I have an intercept, and I have to kind of figure out what my intercept is going to be. I'm just going to calculate this by looking at the differences between these. It looks like it changes a little bit. Here it's about 7. Here it's about 7. Well, maybe about 7. So would it be reasonable to say that this intercept was around 3? You guys think? 3? So I'm going to say plus 3 seconds. That's kind of odd, right? If the mass is 0, it takes 3 seconds for it to travel 1.5 meters. Maybe that's a problem for calculus, right? Maybe it actually curves pretty sharply when something gets lighter. How would we know what happens down here at the end? How could we figure that out? Can you think of something that would have a very, very small mass as a sphere? How about a ping pong ball? Like, what if we measured the mass of a ping pong ball and then threw that in there, and that would tell us what happens down here? Because I'm unconvinced that it would take 3 seconds for something with no mass to travel. But maybe that's telling us about the speed of the water. Anyway, so if we write a clear sentence that describes the relationship between mass and time. So what you need to do here is look back. You guys remember that handout way back here? This written relationship is what you're looking for there. So when we have something that's a line that says, as x increases, y increases proportionally. So I can use that as a framework for writing a sentence about what's happening in this equation. So I could say, as mass increases, time increases. So we get that right off the handout. You guys have any questions about number 2? No questions? Okay. So let's do number 3. A student performed an experiment with a metal sphere. The student shot the sphere from a slingshot and measured its maximum height. The sphere was shot 6 times at 6 different angles above the horizon. What's the relationship being studied? All right, so let's think first. I actually like to do these 2 questions first. What's the thing that the student was changing? Any ideas? Yeah, Sam. Yeah, the angles, right? So let's see the angle. And what was the student measuring in response to the angle? It's funny to have the band on, right? Have them on, have them playing. What was the student measuring in response to the change in the angle? Anybody? Yeah. The height, yeah. And so when we're looking at what's the relationship being studied, we're looking for the relationship between angle and height. What things do have to be held constant through the experiment? What things can't he change? I can think of 2 things he has to make sure he keeps the same. Sam. Yeah, you have to keep the ball constant. What else? What do you change when you want to shoot something a different distance with the slingshot? Besides angle. Yeah. How hard you do it, yeah? So you can measure things like how far you pull it back and make sure that the pullback is always the same. Thanks, band. All right. Do you guys have any questions about number 3? That's just how to set up an experiment kind of stuff. All right. Number 4, what kind of relationship does this graph suggest? This, again, is just going back to that handout. So you guys see a curve, right? This to me looks like this one down here where we've got a relationship of y squared versus x. So it looks like the square of x is proportional to y. So I wrote the square of x, age, is proportional to y, accidents. What variables would you plot to linearize the data if you wanted to turn it into a line? So if we know that the square of x is proportional to y, we can look at our handout and it says graph y squared versus x. So instead of graphing y versus x, we're going to do y squared versus x. You don't have to actually do it for this problem. You just have to say how you do it. Questions? You guys doing okay and just being quiet today? Yeah. First period's like that sometimes, right? All right, next. Consider the graph at right. Maybe you guys have been considering the graph at right. We're going to write a mathematical expression that describes the relationship between scholarships and effort. This is what we would expect, right? As your effort increases, the amount of scholarships you earn also increases. If we're going to write a mathematical expression for that, we would write scholarships in dollars is equal to, and we're given a slope here. It says $500 per application. Per application times the effort in applications plus our y-intercept is 0, which is disappointing. It means that if we put in no effort, we won't get any money, right? Disappointing if you're trying to get scholarship money. So the interpretation for the y-intercept is that no effort results in no scholarships. If we use the equation, how many applications would you need to earn $8,000? So here we're going to use our equation to solve this. We're going to say if we want $8,000 for school and we can earn $500 per application, how many applications do we need? We're going to solve for applications. And to do that, we're going to take our 8,000 and divide by 500. And we get 16. You need to do 16 applications to get $8,000. When I went to college, that would have paid for Wright State for a year. I'm not sure what it is now. I think it's a little more. Okay. For these, you guys have any questions about number 5? No? All right. For these, it says describe how you would linearize the graphs. We don't have to actually linearize them. It just says describe how you would do it, and then write an equation that would describe the straight line that you produced. So again, this is just looking back to that handout. Got my handout. All right, so there's my handout. So if I have a graph that looks like this, what I'm going to need to do is graph y versus 1 over x. And then when I do that, the equation that I'm going to end up with is going to be something like this. Next one, curves up away from the origin. I need to graph y versus x squared. And my equation then is going to look like y equals slope times x squared plus b. Lastly, curve down at the bottom, I would need to graph y squared versus x. And my equation is going to be y squared equals mx plus b. You guys have any questions about those? Okay. On the back, and these were kind of elaborate. So here's a graph that compares the amount of time it takes a planet to orbit the sun versus the distance the planet is from the sun, measured in astronomical units. And this is 1 astronomical unit is the Earth to Sun separation. And so an astronomical unit is the average distance the Earth is from the sun on any given day. Sometimes, of course, it's a little bit more, sometimes it's a little bit less. But generally, we describe astronomical units in comparison to how far we are from the sun. So if we were going to make a test plot to try first, we could look at the fact that this kind of curves up. Let's see, I'm going to draw the color so it's a little bit easier to see. So it kind of curves up in a way. And the first thing that I would do is I would take a look at my other charts, and we've got it, we just copied them all right here, right? I would need to graph y versus x squared. So that's the first thing I would do. I would graph y versus x squared to see what happens. Again, here we're not asked to actually do it. In this case, it turns out that it takes several of these before you end up with a linearized plot. So you guys take a look at this down here. Down here we have radius cubed, right? And then on this side we have period squared. So this had to happen a couple of times. You know, there had to be a squared for each of these as those test plots were generated. And remember, Kepler did this by hand. He didn't have a computer to use. But we end up with these kind of funky units on the side. And it says, write the equation for the graph below. And does the same equation apply to the graph above? All right, so let's write the equation first. This thing is a line, so we know that we're going to be in the form y equals mx plus b. But here our y is orbital period squared. So for y, we're going to have our period squared in years squared is equal to our slope, which is 1 year squared per astronomical unit cubed, times r, which is our radius, cubed, right? So we don't really need to do much about it. As long as we can replace things in there, we can figure this out. Plus, our intercept is 2.692 years squared. Oh, sorry, I crunched that in there. That's 2.692 years squared. Does this equation apply to this? Did we find the equation for that line? What do you guys think? What would the equation for that line look like? Yeah, so this equation does describe this line up here, right? That's why when we look at the handout, way back here, right? When we look at a graph like this, we would say this isn't y equals mx plus b. This is y equals m over 1x plus b. The reason that we can confirm that this equation is because we linearized it, and we took the new axes and figured it out. And this is what scientists do a lot of the time when they're deriving equations, is they take something, they linearize it, and they use the value of the graph with the straight line to find the equation. It's the same thing that you guys did in worksheet number 1, where you were finding the equation for your original graph based on your original data by linearizing the data and then deriving the equation. So some of these are a little bit easier to see than others. But here you've got something that's got an inverse relationship. And it's tricky to figure out the values that go into the equation for an inverse relationship unless you do the linearization, because that's what helps you figure out what the constants are.